This is the second video on relativity, where we're now looking in a bit of detail at time dilation in particular, and how length contraction and the mass increase work. So in the previous video we saw that Michelson and Morley had the thought experiment that showed that there is no ether, or the thought experiment was with the boats crossing, and then they did the actual experiment using light, and it showed that there is no ether. And Einstein then based his special theory of relativity upon the two assumptions that c is constant, the speed of light. We used a slightly larger drawing there, that c is the fundamental limit of the speed of anything in the universe, no matter what the frame of reference, and that there is no absolute frame of reference, which is where the idea of relativity came. So everything is relative in position or to other things. Okay, so anyway, time dilation. If you consider there's all these cool little thought experiments, but if you consider this other one, we've got a atomic clock of some description with a distance spacing, and it's shining a beam of light back and forward between it, so it's just continually bouncing from back and forward between it. Now they're mirrors, if you like, at either end, which allows this to happen. This is roughly how lasers work, by the way. They amplify, the light amplification by stimulated emission of radiation occurs by sending light beams back and forward between two reflective surfaces. But anyway, this light beam bouncing back and forward is used to measure time passing for an atomic clock. Now if we move this clock to the side, you would, if we were taking this as a frame of reference to the background, the light beam would actually be doing a zigzag kind of pathway as it travelled, because we've added that horizontal kind of velocity to it, if you like. So now if we, and it's bouncing off the mirror because the mirrors are moving at the same time as it hits. Now what we might have is a stationary observer outside. From their perspective, the distance that the light beam has covered has increased from the stationary observer. But from the inside view, the distance has stayed the same. So that what that would seem is that the stationary observer, the amount of time taken for the light to travel those distances, also had to increase, because the speed of light is constant. So that therefore means that c, or the speed of light in this case, has slowed down. It had to, because velocity, that's your velocity, is distance over time, and your distance covered has increased, but your velocity hasn't increased to match it, to make it work. So yeah, your time has had to follow that, think that through a little bit. But here we go, from the perspective of the light, and this is where it gets kind of weird. From the perspective of the light, up the top here, everything stayed exactly the same. So distance, time, and the speed of light have all stayed the same. But in this case, the speed of light hasn't changed. That's why we're getting confused with that. Yeah, in this case, this is the time dilation, where it seems to take longer time to the stationary observer. And the classic twins paradox, here's our twins, if you had one of them travelling at the speed of light inside here, to them time has passed like normal, but to the outside person time has decreased, time has slowed down. So it seems that this person hasn't aged during the course of this travel. And the twins paradox is when one of them travels at the speed of light away from another one for a period of time, and then when it comes back, when the person comes back, they are still young, but this person has become older and grown a beard or whatever, become all grey. Anyway, that's the twins paradox. I'll put a link to some Wikipedia articles and stuff for you as well. But very, very awkward Because if you're looking from the perspective of the person inside here, it's because they were going fast that it's affected the time. It's not. I mean, from their perspective, when they both get back, they'll look like this as well. But yeah. Anyway, length contraction. What seems to happen with length contraction? This is all really weird, and I'm sorry if I'm tripping over my words or contradicting myself by accident. It is weird. That's my disclaimer for this, and you can explore more on the Wikipedia article I'll give you a link to. But just be aware that these things occur is the main message. Length contraction. From the stationary observer, who, if they could watch someone travelling in a little car or buggy or something, they would see that little buggy getting smaller the faster they went, or the length, that distance would be getting smaller. And from the perspective of the person in the car, if they're looking at, say, power lines going by, the power lines would appear to be getting close together, but they would stay at the same size. It's all very strange. And I don't know exactly how that adds to the time dilation. If you consider time dilation and length contraction at the same time, I don't know, maybe the length contraction leads to the time dilation, because if they're travelling at the speed of light, they'll cover a greater distance because the distance they're covering has shrunk. But yeah, anyway, think about that some more. The mass increase, however, that's just another interesting little consequence. It takes energy to accelerate things, and the more they accelerate, the more energy it takes. And what happens is the faster they get, the more mass they have. So the closer you accelerate something to the speed of light, the more mass it has, and therefore the more mass it has, the more energy it takes to accelerate it. And it works out, this is a nice one for, if you recognise it, that energy put in is equal to the mass of the object that you're speeding up times the speed of light squared. And I think you've seen that before somewhere, E equals mc squared. That's Einstein's famous equation that relates energy and mass and shows that mass and energy are the same thing, and that constant of proportionality is the speed of light squared. So you can work out how much mass something will gain as it approaches the speed of light well, you can work out how much energy it takes to increase its mass by a certain amount. Yeah, this stuff is just mental. It doesn't really make sense, but it does make sense if you're Einstein. There are formulas to do with these, but I'm not going to get into that. But I will say that there is a lot of experimental evidence to show that this stuff really works. And I'll give you one example from the textbook that I have right in front of me, and that's about muons. Muons are subatomic particles. They can only really experiment with all this stuff using subatomic particles. I think the measuring ability is getting better and better, but it's still, they have to deal with subatomic particles because they're so small, and it's easy to accelerate them in particle accelerators, like the Large Hadron Collider. And Large Hadron Collider, there you go. And these muons, anyway, are subatomic particles, and they're only supposed to live for a short amount of time. You know, their half-life, we talk about radioactivity, but some particles are naturally unstable and will decay into light or into, what do muons disappear into? Book doesn't say, but they decay into whatever else they decay into, maybe photons. But they actually travel. They should only go a particular distance to there, but they actually go all the way to here. That is, we shouldn't be able to, if they're coming in from background radiation in space and the radiation that's naturally around there, they should hit the Earth's atmosphere and stop after, 600 meters? Yep, 600 meters, due to they've got a limited amount of time that they'll survive, and they can come all the way down to the Earth's level, the surface. And they do that because of the time dilation and length contraction, which allows them to do this. So, awesome, very cool. Now, just something interesting to throw out there. We have this pervading theory of the Big Bang, and I haven't really heard anyone talk about this, but I did hear it raised once, and that's the Big Bang was said to expand, everything would expand really, really fast, that creation of the universe. And what I'm interested or curious about is how does time dilation and length contraction and mass increase affect all of that? Because it couldn't expand faster than the speed of light if Einstein is correct with this limit being held to. But this is the expansion of space itself, the empty space, which is not nothing, it's empty space, which has energy. And just wondering, we've got an age of the universe of, I think currently it's about 13.7 billion years. I'm just wondering how they could work that out and take into account all these relativistic effects. And that's something that might keep Stephen Hawking up at night. It doesn't keep me up at night anyway, but it's very interesting to think about these things. And I raise it so that I hope you get interested and might want to explore something like this to further fuel your passion for science and physics. Thanks anyway.